Hello everyone, welcome back to our YouTube channel Becoming a ROS Developer. I'm Desire, and today we've got Katia, who has just completed the course ROS2 Basics using Python, and she will be giving us a presentation of that. So without any further ado, let me hand over the platform to you so she can begin her presentation.
Hi everyone. So now I start my presentation. Can you see it?
Yes, we can see your slides.
Okay, perfect. Can I start?
You can go ahead, Kasia.
Okay. So, good morning everyone. Thank you for joining me. Today I will present the ROS2 development for the ROS2 Basics in 5 days. The course that it is in Python. Just to briefly introduce myself, I am Katia, and I'm currently working as a robotic engineer for Adaptive Reply in Italy, in Turin. So the goal of this work is to design a modular robotic system that makes effective use of the three main ROS2 communication paradigms, so topics, services, and also actions. The application scenario is a mobile robot that is able to autonomously detect a wall, align itself at a desired distance, and also follow the wall while moving. And at the end, record its trajectory during the execution. Briefly, the agenda it is divided into three main sections. So the first one is about topics, the second one about services, and the third one is about actions. This structure is not arbitrary. It reflects the decomposition suggested by the exercise itself. So I decided to follow it in order to explain step by step how I approached and solved the problem. And each section introduced a different ROS2 communication mechanism motivated by the nature of the task it is used for. So continuous reactive control with topics, finite well-defined procedures with services, and also long-running tasks with feedbacks using actions. Starting with the first one. Starting with the first one, the objective is to make the robot follow a wall on its right-hand side while maintaining a fixed distance of 0.3 meters. As you can also see from the GIF that is on the right side of the slide, I took it from the deconstruct site exercise. This task, this is the side behavior. This task comes with several challenges, so maintaining a stable distance from the wall while moving forward, detecting and avoiding obstacles in front of the robot, and also handling transitions such as corners or changes in wall orientation. From a control perspective, this is a classic reactive navigation problem. So now I explain my solution. In this case, I develop a ROS2 node, which is composed of a subscriber, in this case the laser scan subscribers. I of course need the data of the laser to detect the obstacle. As we know, the laser scan, it gives all the measurement of the laser, so with all the degree around robot. But for this use case, I just consider the front area, so the front ranges, the front measurement, and just one measurement for the right for the right side of the robot, so to detect the distance with the wall. Why I use that? I use like the front to detect the obstacle in the front. Also, if I detect the corner, so the other wall, and the right to measure continuously the distance from the wall. So this design choice keeps the perception pipeline simple, efficient, and also robust. Then, of course, inside the same node, I also consider another topic as a publisher, so the command velocities to, of course, command the robot. And at each incoming laser scan, the linear and the angular velocities are updated according to a small set of control rules, as we can define that. So I consider the front distance. If it falls below a threshold, then the robot turns to avoid that obstacle. In this case, the angular velocities was bigger compared to the other case, since I want the robot to quick avoid the obstacles, to quick turn around. Then I check the right distance. So if it is too small, then the robot steers to the left to avoid going against the wall, of course. If it is too large on the other side, it is on the right to avoid going too far away from the wall. And if it is...
just a reminder, Katia, you must understand you have got about 17 minutes left with the robot, so you might want to show the implementation first in case you have got more slides to go through.
I think I will be in time, but if you want, I first...
if you're sure, let's go.
Show the demo. Okay, so I first show the demo and then I continue explaining if you have any question. Okay, right. So can you see?
Yes, we can see it. Yes, just enlarge the stream window a bit.
Yeah, no, I don't want that. Okay, perfect. Okay. So as I was saying, I moved just a little bit the robot because it was too nearby this obstacle, so I don't want it to interfere with my program. So okay, I already sourced it, but I do it with this again. Now I launch. Okay. Okay, now I first show you and then I continue explaining.
No worries, yes.
As output, okay, now the robot is detecting the wall. Okay, perfect. It's going, okay, this is, it's blocked, but okay.
Just click on it, it will start playing. I think it's paused.
Oh yeah, I'm sorry, it was my fault. Okay, now I pause it. No, okay, there is a bit of delay. But now as you see the feedback of the action server. And now as you can see, the robot is correctly following the wall, maintaining the distance. And when it detects the corner, it turns and then it continues following the wall. When it arrives at the start position, then you will see that the feedback will stop.
Okay.
Okay, it stopped.
But does it manage to stop? I see it keeps going.
It stops just the action, not the process. As I understood it, I thought that just the action should stop, not also the robot. Maybe I misunderstood this point.
No worries, no worries. I was trying to find out, did you manage to implement the stop mechanism so that it knows when it gets to the starting point?
Yeah, because I saved the start position and then I see the difference from the start position.
Okay.
In the action server.
Okay, so it was supposed to work, right? You've got that implementation done.
For the action, yes, not in the wall following. I mean, I just stopped recorded the point, so the trajectory.
Okay, so you're just recording the, let's call it odometry, right? You're just doing odometry, but you're not using it
exactly.
to stop the robot.
I just record. Exactly.
Okay. All right. Let's go on.
I mean, I can just add a publisher to stop the robot when I got the response.
Yes. Ideally, yeah, you could do that. That's what I wanted to understand, if you had any form of mechanism.
Yeah. I'm sorry. I just misunderstood the question. Not the question. The exercise. I thought that it just needed to stop to record the odometry, not also the robot.
All right. So no worries. So let's continue the slides.
Okay. Thank you. Okay. So I was at this. Oh no. Sorry. Okay. Where was it? No, I was here, but okay. So here I was just showing you a video, but in this case it was just a wall following. I show you this video just in reality to introduce you the problem. Since in this case for the wall following, I needed to put the robot at the side position, otherwise it will not correctly follow the wall. And that's why we introduced the second part, that is the ROS2 service. Because in this case, if it goes to the next slide, okay, perfect. Because in this case, so the goal of this this section is to make the robot automatically detect the closed wall, align the robot with it, and also position it to a distance of 0.3 meters on the right side. This is also a fine, well-designed procedure, which makes the service more appropriate abstraction than a topic. Also, in this case, I took the GIF in the right side from the deconstructor, and it is the desired behavior that we expect. So in this case, for the node how it is composed, I of course develop another node which contain a subscriber and a publisher. Also in this case, the laser scan, and also the command velocity scan. This is because I of course need the sensor, and I need to command the robot. And then I have the service which is called find wall. For this service server, I need to introduce a custom interface. So I develop another packages just for these interfaces, for these custom interfaces. This is because when the service is triggered, the callback executes the complete find wall procedures and returns a Boolean flag indicating successful completion. And from an execution standpoint, I used a multi-thread executor with a reintrad callback group. This allows laser updates, motion commands, and also service execution to run concurrently without blocking each other. The service execution is divided into 3 sequential phases. Just like before, talking about the service execution, I put a filter on the measurement for the sensors, since I needed to do that because I noticed some difference from the simulation and from the real robot execution. This is because from the real robot execution, I noticed a bit of maybe noise, so it was not that precise. So I added a filter, and with the filter, it was correctly moving. Also, in this case, I put this video, but I mean, you already saw everything.
What values were you filtering? So your filter, what error points does it capture? How do you know this is an error and this isn't?
No, sorry, can you repeat?
What values are you capturing as invalid for using your filter?
Yeah, because sometimes I got like the infinite value. And or otherwise, if I was like if the distance was too small, like also really too small. So I noticed this kind, especially when I started the service. So that's why I use this filter. So I consider like a sort of minimum. Also because I noticed that there was noise. I mean, not noise, but a lot of error when there was obstacle that maybe it was not in that position, but was also like nearby the wall. So I use this kind of filter for that reason. Okay. Because just to explain how I think about the server, I get the first measurement from the sensor. So I detect where is the first, I detect the index in which I got the minimum distance. And then I rotate my robot to make the front of it to coincide with the minimum that I found. But then I also consider the measurement to make sure that I was going to the right measurement, to the right minimum. So this is like the rotate approach. Then there is the approach phase. So once I am at the right position, I move forward to the wall about at a distance of till I am at a distance of 0.3 meters, and then I align to the robot. So I move. I time the move to the right hand side. So I move over 90 degrees. It means timed in the sense that I estimate a time and to obtain like the 90 degrees orientation. This could be, of course, like make more robust with a controller, for example. But for this case, I just use a timed. So the definition of velocities. So
can you show me where this is done?
Yes, of course.
Yep.
Okay, Oh, okay, I'm ready to go forward. Until just a moment. That's not that. Just wait. It's last part. Rotate on the right. It's here. Okay, it's here. So I decided for an angular speed. Then this is like the time that I decided, and then I just published the command to rotate like small rotation over time. And then once I'm here, then I just stop the robot. And then I check if I'm in the right orientation.
And I see also your robot, when it goes around the corner, it uses it doesn't stop and rotate, but it has got some linear velocities as it rotates. Can you explain a bit why you chose to do it that way, or how did you do it?
Yeah, this is in the wall following mode. So in the first node, it's here. Yeah, sorry, there was. It's here. Okay. Okay. To be honest, because I noticed, I mean, just for a preference point, I mean, just when you try and you see things, I think that was smoother if I also added the linear velocity and not just rotate and then it starts. So just to make it smoother, for that reason.
It's a very valid point, and it does perform very well. So I would say well done on that bit.
Thank you. So that's what the reason.
And did you use any form of controller to control the distance that it keeps between itself and the wall?
No, to be honest, no. So, but I mean, from a controller, from a robotic point of view, it should be more robust with the controller. But I decided not to use that just because I'm more focused on the ROS structure. So just for this reason. But of course, like the controller was, I mean, I should say for robust.
I mean, for what you've been doing, right? For what you did on this one, it seems like you actually implemented a controller, which means you did it very well, right?
It was just really a lot of experimentation.
So it's empirical.
I mean, yes, exactly. At some point, I was a bit struggling, and I was deciding to add the controller, but then I thought maybe I'm just overcomplicated things. So that's for this reason I did not implement. But maybe I mean, for robust reason, it's better to use that. I think.
Yeah, you could say that, but I always prefer simple and efficient than complex. So for this task, I think this is very much appropriate. Maybe for more complex systems, perfect. I'd say yes. But the other thing that I want to know is why did you choose to consider only one index, right? That is like perpendicular to the robot. And did you just try and figure out that it was working that way? Because other people use a 45-degree index and a 90-degree index, right? Did that come across?
Yeah, I also so I decided to use just one ray to be really sure that the robot was perfectly perpendicular to the right side. But it was I was considering also just very few ray also for the front, and of course for the simulation was okay. But for the real robot, I noticed that there were differences. Luckily, for also in the real robot case, in the real use case, one ray for the right side was enough. So I'm happy about that. Otherwise, I would have, add other rays also for the right side. But since I was also combining the front with the right, I think that these two combining together make the whole program robust, I would say.
What do you mean combine? So, and are you saying you can explain in more detail?
Because like I was monitoring the front, so to avoid obstacle, and also the right. So combine in sense that since I was checking on both sides, I was sure that, I mean, considering us only just one ray in the right was okay, because I had the full control on the front. So I was sure that if I'm going in the right direction, I cannot like go that much away from the wall in the right side. But I
Okay.
mean, also in this case, as just to, I mean, also in this case, would be better to use more ranges, more measurement also from the right side, of course.
Yeah, so again, it's a trade-off, right? I quite like this
Yeah,
because it's simple
exactly.
and it does a lot of very good things without not taking too many things. However, taking a range into consideration makes it a bit more robust, but you have to ask yourself, do I need that robustness using this way, or I
Yeah,
could just
exactly.
have. So yeah, this is very well done. The other thing I also want to know is when you're trying to monitor your front index and your right index, for example, is that happening in the same loop, or you are checking them using different loops or different branches in your program? Can you show me where that is
Mm,
happening?
yes, it is also in the word following, but in this for the word following, I did not use a different loop, so I just use a single thread executor in this case, if you mean like that.
Um,
Um, yeah, yeah. I'm
so
sorry.
I
Just
mean, are you
it's
checking
here. It's here
both booleans? Yeah, that's what I want to know. Are you checking like the
in
validity
the laser callback.
of both of them? Yes, in one cycle. Yeah, it looks
Yes,
that way.
exactly.
Okay.
Yes, yes, yes.
Okay, very,
And as you
very
can
nice.
see, I just hard coded the ranges
Mm.
based also in this case on the ex I mean, it's empirical also in this case.
Okay. So
So,
if
no,
you
sorry,
run into
continue.
yeah, okay, so if you run into a case where the index that you're checking is actually not valid just because of some noise, for example, because if you are working with a lidar that gives you, let's say for this robot, about 450 indexes, right? If you get your your index at the 90-degree point being a certain value, if that value happens to be invalid for some reason, did you run into that case?
Luckily, no.
Okay, all
No,
right.
no. To be honest, no. It just happened for the front case. I don't
How
know
often? How
why.
often for the front cast?
For the rear case, I mean, before the filter that I had,
Mm-hmm.
uh, always. I don't know, but just at the beginning, I don't know why.
Just at the beginning. Okay.
Just just at the beginning for a few seconds, then it was okay.
Mm-hmm. All right. All right.
So
Very.
that's why I noticed that. But I mean, also because I was like, okay, in simulation, it's everything working really fine.
Mm-hmm.
Then I went to the real case and it was a mess. But then I debugged and I figured it out.
All
So it was
right.
also funny.
Right. All right. Very, very, very nice implementation, Katia. Thank you so much for making such a
Thank you.
wonderful presentation. So, what I recommend is just hang on and
Sorry, can you repeat?
can you just wait for me a bit and we will
Yes, of
finalize
course.
here. Yes. All right, everyone. This was Katia's presentation, and a warm congratulations to her for the job well done. I would like to encourage all those of you who would want to try this course to do so, and you can also come and showcase your work. And until next time, keep pushing your ROS learning. Merry Christmas.